Hello everyone, welcome to lecture 26. Today we'll talk about Bode plots for higher order systems. Let's have a recap of what we have talked about so far. First and foremost, what is the importance of Bode plots? You remember that if I have a system g of s, which is being excited by an input which is a sinusoidal function, the output is also going to be a sinusoidal function at the same frequency. However, it will be scaled and shifted. So in this particular diagram, you can see that I have a g of s, and I'm assuming that I have an input r of t, which is a sinusoidal function, a sine or a cosine, and this is my y of t output. If r of t is a sine function, let's say with magnitude a and frequency omega 0, y of t is going to have the exact same frequency. However, the magnitude is going to be scaled by absolute value of the transfer function evaluated at that particular frequency omega 0 and phase shifted by the angle of the transfer function, again evaluated at that particular frequency omega 0. So this is essentially what we call frequency response of the system, and one of the reasons why we study Bode plots. Now let's remind ourselves of the Bode plots for first order systems and second order systems. Imagine I have a first order system in the standard format that we use, g of s being equal to sigma divided by s plus sigma. I'm interested in g of j omega, which means I would replace all the s's with j omega. So I would have a sigma divided by j omega plus sigma. And you recall from our discussions that we typically scale the frequency with that pole location sigma. So what I would get is 1 divided by 1 plus j omega divided by sigma. That's my transfer function, the first order transfer function. Now for the Bode plot, I look into the magnitude and the phase angle of this transfer function. And you remember that for magnitude, I don't look at just the magnitude, I look into the 20 times log of the magnitude, a quantity in decibels. So in this particular case, 20 log of g of j omega is going to be negative 20 log of square root of omega divided by sigma squared plus 1. Essentially what this is the magnitude of the denominator, this magnitude, and the sign negative that you have in front of 20, that's because this would be the denominator. On the other hand, the angle of transfer function g is going to be the angle of numerator minus the angle of denominator. So that would be the angle of 1, which is 0, minus the angle of 1 plus j of omega divided by sigma. And again, you remember from our discussion on complex numbers that the angle of this guy is going to be the arctangent of the imaginary part divided by the real part. In this case, arctangent of omega divided by sigma, and of course I have a negative sign as well. When we wanted to talk about this magnitude and phase angle, we saw that it typically changes based on the frequency omega in a nonlinear fashion. However, we make approximations in order to be able to draw this by hand. For small frequencies, which we assume small frequencies to be frequencies below 0.1 times sigma. For those frequencies, this fraction omega divided by sigma is going to be very small, so I can kind of approximate g of j omega with 1, which means the 20 log of g of j omega is going to be 0, and the angle for the same reason is going to be 0. These are all things that we have discussed before, so I'm just going through it quickly as a refresher. For higher frequencies, we saw that the magnitude starts dropping 20 dB for each decade. So if I look at the diagram, the Bode plot for gain, for anything below sigma, which is my pole location, I would have a magnitude of 0, and then after that I would have a straight line with a slope which is going to be negative 20 dB per decade. For phase, on the other hand, we look into two important points. So one is for low frequencies, which is any frequency which is less than 0.1 sigma, and the angle is going to be 0. For high frequencies, which here we assume to be 10 times the pole location, this guy here, this quantity is going to be too large, and if it's asymptotically going to infinity, arctangent of infinity would be 90 degrees, and because of that negative sign, I would have a negative 90 for high frequencies. So that means for lower frequencies, I would have a phase angle of 0. For higher frequencies, I would have a phase angle of negative 90 degrees. And then for anything in between, I would have a straight line connecting these two dots, which has a slope of negative 45 degrees per decade, meaning that the phase drops 45 degrees for each decade. Notice here the phase drops from 0 to negative 90. However, this happens over 2 decades when the frequency changes from 0.1 times sigma all the way to 10 times sigma. That would be 2 decades, so the frequency drops by 90 degrees. We had a similar discussion for second order systems. These are systems that have complex poles. And again, you recall the standard format for a second order system, which was omega n squared divided by s squared plus 2 zeta omega n times s plus omega n squared. And then I would replace all the s's with j omega. Here, again, these are things that we have discussed before. For small frequencies, I can assume that this term here, omega divided by omega n, is almost 0. So the magnitude is going to be 1, meaning that 20 log of magnitude of g is going to be 0. The angle also is going to be 0, because if I can ignore this term and this term, it's as if I have a 1 divided by 1, so the angle is going to be 0. For high frequencies, when omega is much greater than omega n, and by the way, omega n is the natural frequency of the second order system, I would basically assume that omega minus omega n squared will overshadow all the other terms in the denominator. So the absolute value of g of j omega is going to be just simply 1 over omega n squared. For the same reason, I can assume that my denominator only consists of this term negative omega over omega n squared, which is a negative number, so the angle of g of j omega is going to be negative 180 degrees. Another key point for Bode plot of second order systems that we consider is typically the frequency, which equals the natural frequency. If you plug in omega equals omega n, you would get different values for the magnitude of g of j omega and the angle of g of j omega. Nonetheless, what we do is we, again, similar to first order systems, we try to approximate this nonlinear Bode plot both for phase and magnitude with linear counterparts. So essentially for magnitude, I would assume that for any frequency which is less than omega n, my gain is going to be 0. Notice that here I'm showing you a gain of 1. However, in Bode plot we look at 20 times log of the absolute value of g. Log of 1 is 0, so that's why you would get a gain of 0. And then for all high frequencies, which would be frequencies greater than omega n, you would get a straight line with a slope negative 40 dB per decade. If you compare this with the diagram that we had for first order system, you notice that in the first order system we had negative 20 dB per decade. So it seems like in a second order system, the effect of both poles will be added together. So each pole is going to add a slope of negative 20 dB per decade. Together that would be negative 40 dB per decade. Phase angle, we can do the exact same thing. For anything below 0.1 omega n, I would assume that the phase angle is 0 because of this. Anything high frequency, which we assume 10 times omega n, anything greater than that, the angle is going to be negative 180, which is this guy here. And in between, I would have a straight line with an angle of negative 90 degrees per decade. Again, remember in a first order system, we had an angle of a slope of negative 45 degrees per decade. And here, because I have two poles, I would get a slope of negative 90 per decade, twice that slope. Again, something that we talked about was that this approximation, this linear approximation, is pretty accurate for damping ratios that are greater than 0.4. If you have a small damping ratio, for example, in this case, which is 0.1, you will see that the actual curve that I'm showing with the dashed blue line here is actually quite different from the linear approximation. You can see the same pattern in this diagram on the right, the phase angles. If you have low damping ratios, you would see that the dashed blue line, it actually deviates away a little bit from this simplified linear model that we have. Finally, we talked about Bode plots for poles at 0. These would be 1 over s, 1 over s squared, 1 over s cubed, and so on. We know these as integrators. So if g of s is 1 over s to the power of n, let's say I have n integrators, n poles at 0, g of j omega is going to be 1 over j omega to the power of n. Let's look at the magnitude. If you look into 20 log of the magnitude, you basically have 20 log of 1 over omega n. And you remember from the basic characteristics of the log function that multiplication is going to be converted into addition. So log of 1 over omega to the power of n is like I'm looking at log of 1 over omega times 1 over omega times 1 over omega all the way n times. This would be as if I would add these together. So that would be n times log of 1 over omega. On the other hand, log of 1 over omega, you again remember from the basic characteristics of the log function, that would be negative log of omega. So the angle is basically, the magnitude is going to be negative 20 times n times log of omega. This would be a straight line with a slope of negative 20 times n dB per decade. What does that mean? That means every pole at 0 is going to add this negative slope. If you have 3 poles at 0, that would be negative 60 decibel per decade. How about the angle? The angle is going to be the angle of the numerator minus the angle of the denominator. A numerator is 1, an angle of 1 is 0, so we can ignore that. Denominator is j omega to the power of n. And again, for angles, we would basically add all these together. So it's as if I would be adding the angle of a single j omega n times. J omega is a purely complex value, purely imaginary value. So angle of j omega is going to be 90 degrees. If I have n of those, so it's going to be negative 90 times n. You can see that this in this situation, the phase angle is actually different from what we have seen before in first order and second order systems. The phase is basically going to be constant at negative 90 times n degrees. Now, so far we've been only reviewing things that we have talked about before. Let's talk about a few new things. One thing we didn't discuss was how a 0 would affect the gain and phase of a transfer function. First, we're going to focus on zeros that are in the left half plane, so the left side of the j omega axis. In order to do that, we're going to borrow what we know about the behavior of a pole. Imagine I have a single pole in the denominator, some s plus sigma. If I replace s with j omega, I would have sigma plus j omega. That would be a complex value. That complex value will have a magnitude and a phase angle, which I'm showing it here. So imagine if I have a pole at sigma, this pole would be represented by a complex number which has a magnitude of r and angle of theta. Now, what would happen if this sigma would be a 0 and not a pole? If it would be a 0, that means instead of having a j omega plus sigma in the denominator, I would have a j omega plus sigma in the numerator. So I would be looking into a different complex value. Here I call it S2, which would essentially be the inverse of S1. Inverse of r with angle theta is going to be a complex value itself. However, the magnitude is going to be the inverse of the magnitude of S1, 1 over r, and the angle is going to be the negative of the angle of S1, in this case, negative theta. In Bode plots, we're not interested in the absolute value of the magnitude. We're interested in the 20 times log of the magnitude. So if I'm looking at the 20 times log of S2, I am looking into 20 times log of 1 over r. And again, from the basic characteristics of the log function, you remember that log of 1 over r is going to be negative log of r. So I can write this as negative 20 times log of r. If this was a pole, the magnitude would be 20 times log of r. Since it is a 0, it will be negative 20 times log of r. So for the gain, consider this example, this first order system. For the gain, if it was a pole, I would have a gain of 0 before, all the frequencies less than sigma, and then I would have a straight line with a slope of negative 20 dB per decade. Because it is a gain, it's going to be the inverse of that, meaning that the slope is going to be now 20 dB per decade. Phase angle can again be compared by just multiplying the phase angle of a pole by a negative 1, let's say. Again, you remember if I had a pole, I would have an angle of 0 for anything less than 0.1 times sigma, a straight line, and then a line with a slope of negative 45 per decade, and then a straight line at negative 90 degrees. Because of that negative sign in front of it, the phase angle for a 0 is actually going to be the flipped version, meaning that for anything low frequency, you have 0. For high frequency, you will have 90 degrees. And then anything in between, you will have a straight line with a slope of 45 degrees per decade. You can extend this discussion to a second order 0. So here again, for all low frequencies, less than omega n, you will have a gain of 0. For high frequencies, you will have a line with a slope of 40 dB per decade. Remember that if we had a double pole, it would be a straight line with a slope of negative 40 dB per decade. This, however, is going to be negative of that, so that's why it's a plus 40 dB per decade. And again, if you recall, for the phase of a second order system, a system with two poles, we would have a angle of 0 for low frequencies, angle of minus 180 for high frequencies, and anything in between would be a line with a slope of negative 90 per decade. Here, on the other hand, for low frequencies, similar to poles, I have 0. For high frequencies, however, I would get 180 instead of negative 180. And anything in between is going to be a straight line with a slope of plus 90 per decade, negative of what I would get for a second order system. Now, so far we've been talking about zeros and poles that lie on the left side of the j omega axis. What if we have poles or zeros that are in the right half plane? That actually, again, can be analyzed based on what we know about zeros and poles on the left half plane. Imagine I have a pole in the left half plane, which would be a plus jb, or 0, for example. If I have a pole or 0 on the right half plane, I would basically get an a negative jb. Remembering what we know from complex values, we know that the magnitude of this guy is going to be equal to the magnitude of the other guy. So in terms of magnitude, nothing changes. If I have a 0, remember that we have already talked about zeros and poles in the left half plane. If I have a 0, I would get a plus 20 dB per decade, and for a pole I would get a negative 20 dB per decade. So if I have a 0 or pole on the right half plane, it's going to be the exact same magnitude slope, because again, based on what I just showed you here, the magnitudes are going to be the same. So regardless of where the pole or 0 is located, the slope is going to be the same. For 0 in general, the magnitude is going to be plus 20 dB per decade. For pole in general, it's going to be negative 20 dB per decade. The phase angles, however, are going to be different because, again, notice here for A plus JB, the angle is going to be arctangent of B over A. For A minus JB, the angle is going to be arctangent of negative B over A, or negative arctangent of B over A. So it's basically like the other one with a negative 1 multiplied by it. So since we know that every 0 in the Bode plot for phase angle adds a slope of 45 degrees per decade, if that 0 lies in the right half plane, the slope is going to be negative 45 per decade. Likewise for poles, if it's in the left half plane, the angle is going to be negative 45 per decade and plus 45 per decade if the pole is located in the right half plane. I understand that this might be a little bit confusing. So one good way is to actually remember this table or write it down somewhere. And once you look at a particular transfer function, immediately identify if the poles or zeros are actually located on the left half plane or right half plane. Based on what you see in the transfer function, then you can see what the slope is going to be for either the magnitude or the phase. All right, so up until now, we've been talking about individual systems. A first order system which has only one pole, second order system with 2 poles, or first order 0 or second order 0. In practice, however, we usually have systems that consist of multiple zeros and poles. What we do to these systems is we break them down into a multiplication of lower order functions. Let's look at a hypothetical example. Let's say I have a function g of s, which is a combination of 4 transfer functions, g1 times g2 times g3 times g4. If, for example, all these g1, g2, g3, g4, if all of them are first order poles, that means g of s is going to be a fourth order system. On the other hand, it is possible that g1, for example, is a 0, g2 and g3 are a pole, g4 is a 0. So that would be a second order system with 2 zeros. So essentially you can break them down any way you want, but basically what we do is we break them down into first order polynomials or second order polynomials, either in the numerator or denominator. So we basically want to have individual zeros and poles. We will have a couple of examples that if it's not clear now, it will be clear shortly. So for now, just assume that I have a transfer function, which is a higher order system. I break it down into multiplication of some functions that are lower order. Now, if I have g of s, multiplication of these 4 functions, for the magnitude, I'm looking into the log of g of s. Again, one of the benefits of log is that it converts multiplication into addition. So 20 log of g of s is basically going to be 20 log of g1 plus 20 log of g2, 20 log of g3, and g4. Likewise, for phase angles, again from our previous discussions, you remember that if I have a multiplication of a bunch of numbers, numerators, denominators, the angle is going to be the angle of everything in the numerator added together minus everything in the denominator added together. In this particular case, because I'm kind of, using a general situation, I don't know which one has a pole, which one has a 0, I can simply assume the angle of g of s is going to be the summation of the angles of these individual functions. So this is actually a very interesting condition that we can use for higher order plots. Seems like if I can break my higher order system into lower order systems, ideally first order and second order, I can just look at the Bode plot of the individual items and the phase angle, phase plot of individual items and just add them together. Once you add all the Bode plots of magnitudes of individual terms, you will get the Bode plot of the higher order system. If you add the phase plot of all these individual functions, you will get the phase plot of the overall function g of s. So we use this in order to find the Bode plot of higher order systems. In order to do this, we have to go through a couple of steps. The first step is typically the function that you get is not going to be in the standard form that we use for Bode plots. Remember that in Bode plots, if I have an S plus sigma, I would like to write it as j omega divided by sigma plus 1. That's the standard form. So any function that I have to break it into the standard form. Look at this hypothetical example. I have a g of s that consists of 4 terms, 2 zeros, 2 poles. I have a DC gain k. In the numerator, I have 2 poles, one at negative a, 2 zeros, one at negative a, one at negative b. And at the denominator, I have 2 poles, negative c and negative d. In order to write it in this standard form, essentially I should take the first term, s plus a, multiply it by a, and divide it by a. The term that I multiply by, this a, I take it as part of the DC gain. Then I would divide this term by a, so that would be s over a plus 1. Let's look at the second term. I have an s plus b. So what I do is I divide this by b in order to get this standard form, s over b plus 1. However, I also have to multiply it by b. So I consider b as part of the DC gain. I would do the same thing for any term that I have in the denominator. So s plus c becomes s over c plus 1, however, multiplied by c. Again, I take c and I include it in the DC gain. Likewise for d. So DC gain in this particular system is going to be k times a times b divided by c times d. And then I have a bunch of terms that are essentially in the standard format that we usually use for Bode plots. In all of them, I have a j omega over sigma. In this case, of course, I haven't replaced s with j omega, but if you do, you will get j omega over a plus 1, j omega over b plus 1, j omega over c plus 1, and j omega over d plus 1. Now that I have everything in the standard form, what I would do is, based on what we talked about a couple slides back, in order to find the magnitude of the system, I would find the magnitude of the individual terms and then add them together. What are my individual terms? I have a k, which is my overall gain. I have a j omega over a plus 1, j omega over b plus 1, and so on. So my overall magnitude, 20 log of g of j omega, is going to be the magnitude of the first term, 20 log of k, magnitude of the first 0, 20 log of 1 plus j omega over a, the second 0, which would be 1 plus j omega over b, minus magnitude of the first pole, 20 log of 1 plus j omega c, and second pole, and so on. For the phase angles, we would do the exact same thing. The phase angle is going to be the phase angle of the constant term, the DC gain, which is k, plus the phase angle of the first 0, the phase angle of the second 0, minus the phase angle of the first pole and the second pole, and so on. We can further simplify this. Notice here I keep that as, angle k, because it could be positive or negative, and I want you to pay attention to that. If k is a positive value, obviously the angle is going to be 0. If it's a negative value, however, it's going to be 180 degrees. The angle of the second term is going to be tangent inverse of the imaginary part, which is omega over a, divided by real part, which is 1. And we do the exact same things that we've been doing so far in order to find that. So to recap, what we have to do is to find the magnitudes of the individual terms and find the phase angles of individual terms based on different frequencies, and then add everything together. Once you add everything together, you will get the Bode plot for that higher order system. Let's go through an example so it's a little bit more clear. Consider this open loop transfer function that I have. G of s is 2 times s plus 2 divided by s squared minus 1. This system has 1, 0 at negative 2. and two poles, one at +1, one at -1. So it has 1, 0 at the left half plane, one pole at the left half plane, one pole at the right half plane. First thing I do is I would write this in the standard form. Here I have done the numerator first. So s plus 2, I write it as 2 times s over 2 plus 1. Then I break the denominator into two terms, s plus 1 and s minus 1. Notice s plus 1 is already in the standard form. You can think of it as, s divided by 1 plus 1, which is pretty much s plus 1. S minus 1, however, I have to convert it into the standard form. So what I do is I divide both terms by -1, which will give me s divided by -1 plus 1. And then I have a -1, which I would multiply it here. The next thing I have to do is I have to replace all the s's with j omega. If I do that, I would get a -2 by 2, or -4, times j omega divided by 2 plus 1, divided by j omega plus 1 times j omega divided by -1 plus 1. You can think of this as 1 minus j omega. Now, in order to find the Bode plot, I'm going to have to look into the magnitude plots and phase plots of individual terms. We will start with the first term, which is my DC gain. So that's -4. The gain for that is going to be 20 times log of 4. Notice not log of -4, because I'm looking into the absolute value of each term. So 20 times log of absolute value of -4, which is 4. That value comes to 12. So that's the gain of the first term. The next term is my 0. I have a 0 at point -2, which in the standard form I show it as j omega over 2 plus 1. Based on what we have seen so far, the magnitude plot is going to be a straight line with a magnitude of 0 for low frequencies, basically anything less than 2. And then it's going to be a straight line with a slope of 20 dB per decade for higher frequencies. The next term is going to be the pole that I have at -1. Here I would get a line with value of 0 for low frequencies, and then I would get a line with a slope of -20 dB per decade for higher frequencies, anything more than 1. I also have another pole. This one is in the right half plane. Notice here, however, the shape of the magnitude plot is exactly the same. Again, because as I mentioned earlier, if you have a plus jb, it has the same magnitude as a minus jb. So these two guys are going to have the exact same magnitude plot. Now I have to combine all these together to see what the eventual Bode plot is going to be for this higher order system. In order to do this, I have to pay close attention to the breakpoints. What are the breakpoints? These are the points at which something exciting happens. A line with a positive slope or negative slope. In this particular situation, I have two breakpoints. One is the point 1, or essentially frequency of 1 radian per second, and the other one is going to be the frequency of 2 radian per second, essentially this guy and these two guys. So before I get to 1, nothing exciting happens, because I would be essentially adding this portion of all the plots together. I have a 12, which I add 0 to it, I add 0 to it, and I add 0 to it. So before 1, I will have 12. At point 1, this is where the two poles start having an impact on the gain plot. What is this impact? Each one is going to be a straight line with a slope of -20 dB per decade. So it would be as if I have a straight line with a slope of -40 dB per decade. So imagine this is that line. For how long this line continues? Until I get to the next breakpoint, which in this case is going to be 2 radian per second. At that point, I will start seeing the impact of the 0. The impact of the 0 is going to be a line with a positive slope of 20 dB per decade. What did I have before? I had negative 40 dB per decade. So I have negative 40 dB per decade. I add a 20 dB per decade to it. So I would be left with only negative 20 dB per decade. So if I want to kind of distinguish, imagine this dotted line is negative 40 dB per decade. This is going to be the negative 20 dB per decade. So essentially I would have a constant 12 for any frequency less than 1. For any frequency between 1 and 2, I would have a straight line with a slope of negative 40 dB per decade, and anything greater than 2, that would be a line with a slope of negative 20 dB per decade. Let's talk about the phase plot. Again, I would do the same thing. I would look into the 4 different components separately. I have a DC gain, 1, 0, and 2 poles. The DC gain is a negative value, so phase angle of it is going to be negative 180. Then I have my 0 at negative 2. Again, you remember that for a phase plot of a 0, I would have 2 important breakpoints. One, 10 times the location of the 0, the other one, the location of the 0 divided by 10. So in this case, I would have a 20 and a 0.2. Notice we look into the absolute value of the frequency. So I would look into 2 radian per second, 20 radian per second, and 0.2 radian per second. For all low frequency components, I would have a phase angle of 0. High frequency, I will get 90 degrees. Anything in between is a straight line with an angle of 45 degrees per decade. Then I have a pole on the left half plane. Here the breakpoints are going to be 0.1 and 10. So for any low frequency less than 0.1, you will get an angle of 0. For high frequencies greater than 10, you would get an angle of negative 90 degrees. And anything in between would be a straight line with a slope of negative 45 degrees per decade. Then I would have another pole at the same distance from the origin, but on the other side of the j omega axis. So this one is going to be at +1. You remember from our previous discussion that this one is going to have the opposite angle. So essentially, it's like the angle of the first pole multiplied by negative 1. In order to find the overall phase plot, I would have to add all these 4 plots together. However, you notice that the 2 poles, one at +1, one at negative 1, actually have opposite phase angles that cancel each other out. So I don't really need to worry about this one and this one. The only thing I need to do is to look into the phase angle for the constant value and also the 0. The phase angle for the constant value starts at 180, or negative 180 rather. It continues at that point until the first breakpoint, which is 0.2. At 0.2, I will start having a straight line with a slope of 45 degrees per decade. And at 20, which is this point here, I would end up staying at 90 degrees. So at 20, I would have 90 degrees, but I would have to add this 90 degrees to the negative 180. So that would be negative 90 degrees. So anything after 20, I would have a straight line at negative 90 degrees. In between, I would have one line with a slope of 45 degrees per decade. So this is going to be the overall phase plot for this particular system. I must apologize if you hear some noise in the background, some squeaking noise. This is my puppy who is playing with one of her toys. Hopefully this is not too distracting for you. Let's move on to another example just to make sure that we feel comfortable with this notion of higher order plots. The second example that we're talking about is shown here. I have a system with a 0 at 10, in other words, on the right half plane, and a pole at negative 100, the left half plane. First step is to convert this into the standard form. In the numerator, I have s minus 10. I multiply it by negative 10 and divide it by negative 10. So I would get negative 10 times s divided by negative 10 plus 1. That's the standard form. I do the same thing for the denominator. I get 100 times s divided by 100 plus 1. I can simplify this by dividing that negative 10 by 100, so I get negative 1 over 10. That negative 0.1, that's essentially the DC gain of my system. The next step, I would replace all the s's with j omega. So g of this one should basically say g of j omega, not s. So that should be an omega. So g of j omega is negative 0.1 times j omega divided by negative 10 plus 1, and j omega divided by 100 plus 1. So let's look into these three components. Essentially, I have a DC gain, I have a zero, I have a pole. Let's look at how the diagrams look for each of these elements, and then we would combine all these together. So let's look into the three elements individually. I have the DC gain, I have one pole, I have one zero. Let's start with the DC gain. So the DC gain here is negative 0.1. The gain is going to be 20 log of 0.1. Again, I repeat that you look into the log of the absolute value of the gain. So the absolute value of negative 0.1. Log of 0.1 is negative 1, so that gain value is going to be negative 20. Next, I have a 0. This 0 is in the right half plane, so it's at point plus 10. However, as we discussed, for magnitude, it doesn't really matter where you are, in the left half plane or right half plane, the pattern is going to be the same. So here I would have a breakpoint, which is the location of the 0, 10. Anything below that, you would have a gain of 0. Anything above that, you would get a line with a slope of 20 dB per decade. Then I also have a pole. This pole is in the left half plane at point negative 100. This here means that 100 is my breakpoint. Notice this is the positive value of the frequency. Anything below that has a gain of 0. Anything above that is represented by a straight line with an angle of negative 20 dB, with a slope of negative 20 dB per decade. All I have to do now is I have to combine all these together. Again, in order to do this, you would look into the breakpoints. The breakpoints for me are 10 and 100. Before I get to 10, I don't need to do anything. I just look into the gain of that DC gain and see what I have. I get a straight line with a value of 20, negative 20 rather. So before I get to point 10, I will have a straight line with a slope of 0, basically, at negative 20. When I get to the first breakpoint, 10, I would start having 20 dB per decade slope. So that would be 20 dB per decade, and since this starting point is negative 20, that means after 1 decade, which happens to be the second breakpoint, I would get exactly to 0. At second breakpoint, I would have a second line which is having a slope of negative 20 dB per decade. From the previous line, I have a plus 20 dB per decade. From the second line, negative 20 dB per decade. I add them together, that is going to give me a line with a slope of 0. So that's basically how my overall magnitude plot would look like. Let's do the same for the individual phase plots. So for the DC gain, which is a negative number, negative 0.1, the angle is going to be negative 180, constant angle. For the first 0, keep in mind that this is a 0 on the right half plane at point 10. So the slope is going to be negative, as opposed to all the zeros who are in the left half plane with a slope of positive. So here the breakpoints are going to be 0.1 times 10, which is 1, and 10 times 10, which is 100. Before we get 0, for higher than 100, we get negative 90 degrees. In between, we get a straight line with an angle of negative 40 per decade, 45 per decade. Then I have a pole at location 100. The two breakpoints are going to be 0.1 times 100, which is 10, and 10 times 100, which is 1,000. This is a pole on the left half plane, so the slope is going to be negative. Anything before 10, I would get an angle of 0. Anything after 1,000, I would get an angle of negative 90. And in between, I will have a straight line with a slope of negative 45 degrees per decade. This is a good example because it actually shows you quite a few breakpoints. So if I want to find the phase plot of the overall system, I would have to look into all these different breakpoints. Let me use a different color here. So what are the breakpoints? The first breakpoint is 1. This is where the phase angle of the 0 starts changing. The next breakpoint is going to be when the phase angle of the pole starts changing. So that's going to be point 10. Then the next breakpoint is going to be when the phase angle of the 0 stops changing. So it basically settles at negative 90 degrees. And finally, we have a fourth breakpoint, the final breakpoint, which is point 1000. This is where the slope of the phase of the pole also goes to 0. So now we would have to combine all these together. Okay, so first I will start from values that are lower than 1 radian per second. Here I don't have anything exciting from the other two graphs because the pole and the 0, they don't have any phase. The phase angle is 0. So the only thing I have is going to be negative 180 degrees. So let's say this is the line for it. And I stop at the first breakpoint of 1. The next breakpoint is 10. What do I have between 1 and 10? From the first graph, I have a negative 180. From the third graph, I have a 0, so I don't need to worry about that. From the third graph, I have a straight line with a slope of negative 45 degrees per decade. So this would be as if I have something superimposed on my straight line of negative 180. So it's as if I have a negative 45 per decade somewhere like this. The next breakpoint is going to be 10. At 10, I will have one line which is negative 180, one line which has a slope of negative 45 per decade, and the other one which has, again, the same slope, negative 45 per decade. The two slopes will be added together, and that would be negative 90 per decade. So here, this would go with a higher slope. Of course, what I'm trying to show here is not accurate, as you can see, but you get the gist of it. So the first section is going to have a slope of negative 45 per decade. The second line is going to have a slope of negative 90 per decade. When I get to breakpoint number 3, which is point 100, all of a sudden the impact of the phase of the 0 goes away. The slope basically becomes 0, and it stops at negative 90. So the only thing I have is the line representing the phase angle of the pole, essentially this section of the line. So I would go back to the slope of negative 45 degrees, and finally, when I get to the breakpoint, the last breakpoint, 1,000, I would essentially have negative 180, negative 90, negative 90, which would be negative 360. What I've tried to show you here clearly is not super accurate, but you kind of, when you want to do this on the exam or in the homeworks, you have to do this accurately. You have to use a ruler and indicate different points. So you would, for example, indicate, again, let me use a different color, indicate that this line has a slope of 45 degrees per decade, negative 45 per decade. This one has a slope of negative 90 per decade. This one has a slope of negative 45 per decade. And then you would have to find all the individual points. For example, at the first breakpoint, which is this point here, at frequency 1 radian per second, I would get negative 180. Then at the next breakpoint, at 10, I had negative 180, and I also had a line with negative 45 degrees per decade. Since this is 1 decade, I would have negative 180 minus 45, which is going to be negative 225. And then you would have another 90 degrees for the other decade, and so on and so forth. So to recap, what we did in this lecture was to look into Bode plots for higher order systems. and essentially what we do is we break the system into a series of lower order systems, 4 poles or zeros, and then we find the gain plots and phase plots for individual systems, and then we would add them together to see what the eventual Bode plot is for that higher order system.